In this video, we will look at calculating shortest paths between nodes in a network. Shortest paths can be calculated using the analyze.ShortestPath function. The source and target positions are specified, as well as the network to be used. The function will then search for the shortest path through the networking, starting at the source and ending at the target. In the example, one source and one target are specified, so the function finds a single path. The path has been extruded just to aid visualization. Multiple sources and multiple targets can also be specified. For each source, the shortest path to every target is calculated. In this example, one source and 3 targets are specified. This will result in 3 shortest paths, from the source to all 3 targets. The paths overlap at the start but then diverge as they move towards the different targets. Specifying 2 sources and 3 targets would result in 6 shortest paths. 3 paths from each source. Next we will look at how the result data is returned. All the analysis functions return dictionaries containing the result data. The dictionaries will typically have keys with lists of values. In the example, the shortest path function returns a dictionary. The data contained in the dictionary varies depending on the last parameter. Data can be extracted out of the dictionary using the dictionary keys. If paths is selected, the dictionary will contain the actual paths. The edge paths key is a list of lists of edges for each shortest path. The parsi paths key is a list of positions for each shortest path. In this case, there are 3 paths. So each list contains 3 sub-lists. If counts is selected, the dictionary will contain the number of times each edge or position was traversed by the shortest path. In total, there will be 4 lists. The edges key is a list of all edges traversed by all shortest paths. The edges count key is a list of numbers counting the number of times each edge was traversed. The POSIS key is a list of all positions traversed by all shortest paths. The POSIS count key is a list of numbers counting the number of times each position was traversed. The lists will have matching lengths. The edges list will be the same length as the edge counts list. And the positions list will be the same length as the position counts lists. If distances is selected, then the dictionary will contain the distances from each source to each target. These distances are the lengths of the shortest paths. In total, there will be 2 lists. The source POSIS key is a list of all the source positions. The distances key is a list of lists of numbers, the distance to each target position. Next we will look at how some of this data can be visualized. A simple and effective way of visualizing the data is by extruding geometry upwards. The height of the extrusion can be made proportional to the data value being visualized. Adding a gradient color further enhances the visualization, making the contrast clearer. In the examples, we are visualizing edge counts by extruding each edge upwards by a distance that is proportional to its count. In the first example, edge counts for 3 paths are visualized. In the second example, edge counts for paths from one source to all positions in the grid are visualized. In the third example, edge counts for paths from all positions to all positions are visualized. These examples are the same as in the previous slide. However, in this case, we are visualizing position counts. Each position is copied and moved upwards by a distance that is proportional to its count. The positions are then joined up to create polygons. Next we will look at a variant of the shortest path, which we refer to as the closest path. The analyze.ShortestPath function is similar to the shortest path, except that it only returns results for the closest target rather than all targets. In the example, for the source, all positions in the network are specified. And for the target, 4 positions are specified, highlighted by the 4 white squares in the corners. For each source position, the closest path function will find the closest target. Here we can see the results, visualizing edge counts and position counts. The top image shows the extrusion of edge counts. The middle image the extrusion of position counts. And in the third image, position counts have been visualized as columns, which is another alternative way to visualize the data.